Hello again. I'm going to start out this video by talking about the difference quotient. Really, last video I could have brought it up, I just didn't. I'll bring it up on this video. Now this fraction inside here, without the limit, what is this just this fraction that I've highlighted here? This fraction that I've highlighted for the time being is called the difference quotient. And naturally the derivative at x equals c is going to be the difference quotient relative to c here. Okay, so the derivative is the limit of the difference quotient. You may have seen this in algebra. It's called the difference quotient, as I said before. But there's that. Now let's go to, I'm going to go to Excel. Now for any fixed h, you know, this will be the slope of the line. What is this, by the way, guys? Notice this right here can be interpreted, the difference quotient, as the slope of the secant line passing through a point whose x coordinate is c plus h and whose y coordinate is c plus h, and also passing through separately c and f of c. So the difference quotient is the line, and I'll tap that. Let me tap this. Sorry for the delay. The difference quotient is the slope of the line passing through, well, I can't type here. So passing through the Cartesian coordinate c comma f of c, and this line is unique. There's only one of a kind like it, and c plus h comma f of c plus h, and my spacing is a little bad here, but will it let me? I'm afraid to indent it. No, that's good. Okay, so the difference quotient is the slope of the unique line passing through this point right here and this point right here. Okay, as h closes in on 0, now that's for a fixed h. Now, if we let h vary, and if we let h hone in on 0, this slope, the slope of this line, this slope will approach the slope of will approach our derivative value. At x equals c. Because, guys, what's happening is if h wards in on 0, you know, this Cartesian coordinate, this coordinate is moving now. We're letting this coordinate move because h is moving. If h is moving in on 0, it doesn't matter if it's from the left or right. It doesn't matter. H doesn't have to be positive after all. Not at all. But if h is closing in on 0, then this whole Cartesian coordinate here is closing in on cf of c. This is fixed. This guy is still. This is what the point we're interested in right here. And as this guy zones in on this guy, the slope, this guy right here, we're taking, you know, this fraction by itself, you know, we're throwing it in this limit, and it's zoning in on the derivative. So it's zoning in our derivative value, f prime of c. And that's, oops, and I'll have to go get my, put that in the right form. So it's zoning in on f prime of c. So it's closing, it's approaching the derivative value, it's approaching f prime of c. So and this line right here, it has a name. It's called, I'm going to insert this word called the secant. It's an adjective, the secant line. So we call it, the line passing through these 2 points is a secant line, and there's infinitely many secant lines, of course, depending on, you know, you can change points. As h approaches 0, actually there's something else that happens. Our tangent line, or excuse me, not tangent line. Oops, our secant line. Our secant line approaches becomes more and more, our secant line becomes more and more like a like the line that is tangent to our graph at our point. But I need to define tangent line. Now, I've not even really defined this, and I need to do that. And I probably should have done that a minute ago, but it's okay. Let me go ahead and let's go up here, and since I put the cart in front of the horse, proverbially speaking, the tangent line is the line that best approximates the y values of points that are on the graph of f of x and are very close to and are very close in location. Well, what else could it mean? But and are very close in location to c comma f of c. They're very, very close. They don't have to eat, they're not on it, but they're very, very close to it. So, and that's very informal. Now, to give you the real hardcore, the real McCoy definition, the real true definition, I would have to use epsilons and deltas from advanced calculus, and I don't want to do that, okay? If this feels fudgy, it's because it is, but for our purposes in this class, it will do. So the tangent line is the line that best approximates the y values of points that are on the graph of f of x and are very close in location to c f of c. And you know what? This is hollow. The tangent line of the graph of f of x at c f of c. I know it's a mouthful, but I need to say it because it's kind of vague if I don't. If I just say tangent line, you know, you're like, well, what tangent line? At what location? Of what graph? So the tangent line of the graph of f of x, let's just say we have a nice enough function f of x. So the tangent line of the graph of f of x at the location Cartesian coordinate c f of c is the line that best approximates the y values of points that are on the graph of f of x and are very close in location to c f of c, and are let me just say very close to. So they're very, very near c f of c. And I'm not really giving you a definition of what it means to be very close to, but I don't want to go into advanced calc. There is some sweeping under the rug that I'm doing, and I'm doing it on purpose here, okay? So the tangent line of the graph of f of x at c f of c, and I really for neatness ought to do that. So the tangent line of the graph of f of x at c f of c is the line that best approximates the y values of points that are on the graph of f of x. I really should say the graph. Of f. On the graph of f and are very close to c f of c. So I've said the tangent line of the graph of f of x at c f of c is the line that best approximates the y values of points that are on the graph of f and are very close, let me get rid of that, to c f of c. Okay, so for points that are on the graph and are very close to c f of c, the tangent line is the line that passes through c f of c that does the best job of approximating the y values of those nearby points. So for nearby points that are on the graph, the one line that, if we insist on a line passing through c f of c, the line that does the best job of approximating points close to c f of c while still passing through c f of c is the tangent line. Any other line might be pretty good, but it won't be as good as the tangent line. And even if it is good, you know, it won't be as good as the tangent line. So the tangent line, this should come first. The tangent line, you know, of the of the graph of f of x at CF of C is the line that best approximates the y values of points that are on the graph and are very close to CF of C. So that's the definition of the tangent line. And the slope of the tangent line, guess what? It's going to be the derivative. Is the slope of the tangent line of f at CF of C is the derivative. That's the visual definition of the derivative. Now that's the visual definition, but it doesn't do much in the way of actually telling you how to get the numeric value. This up here told you how to get the numeric value. This is the visual definition, okay? So f prime of C is the slope of the tangent line of f at CF of C, okay? Really, we have to, the tangent line, to really give you the true and blue definition of the tangent line, I have to give you the advanced calculus epsilon delta definition, and I just don't want to go there. So let's just take this. So just take this informal definition, and then you can also define the derivative as the slope of that tangent line. The bad news is it doesn't tell you how to actually numerically find f prime of C. I could give you a tangent line, all right, but how on earth would you find the numeric value of it? This doesn't really give you anything to go on. You need this limit up here to get that, okay? Now the difference quotient, now if we go down, the difference quotient is the slope of a line we call the secant line, is just a name call. So the difference quotient is the slope of the secant line passing through CF of C and another point, C plus H, F of C plus H. Okay, that's on the graph. Naturally we defined it to be on the graph by this definition here, because if my y-coordinate is F of C plus H and my x-coordinate was C plus H, it's going to be on the graph just by the nature, of F, of how we defined it. Now, as H is going to 0, now we're going to let H move. Now, H, here H was fixed. So if we let H move, and if we let H move to 0, here H is not moving, here H is moving. So as H moves to 0, our secant line is going to change. It's going to tilt, because now this point is now moving. It was still, at first it's still, now let's let this point here move. Let's change its role from still to moving. As H is moving to 0, so this point here, that's going to cause this point to move, and it's going to move toward this point, and our secant line is going to continuously change. And as H gets very, very, very small, when this point right here is going to get arbitrarily close to this point, and the slope of this secant line is going to get arbitrarily close to the slope of my tangent line. So the slope of my secant line, which is my difference quotient, by the way. After all, the slope of the secant line, remember from algebra, I do f of c plus h. To get the slope of the secant line, I do f of c plus h minus f of c over, well, c plus h minus c is just h itself. So the slope of the secant line is, well, let's just go ahead and type it in. M for slope equals, M is just a name tag. So it's f of c plus h, f of c plus h minus f of c over, well, I need to do c plus h, and then I need to do minus c. The difference I do the difference of the y coordinates over the difference in the x coordinates. But guys, the denominator is kind of silly because those c's are just going to cancel, and that leaves you h. There's our difference quotient. The numerator we're not going to mess with. Okay, so there's that. The difference quotient is the slope of this secant line. So really, what we do is we go ahead and construct this secant line passing through these 2 points, and we note that the slope of that secant line is, well, our difference quotient. Okay, and you know what? Let me cut this. I don't want to put the cart in front of the horse, so to speak. Let me cut this and then put this right here. Now, as h goes to 0, our secant line becomes more and more like our tangent line to our graph at CF of C. And I really should say it's the graph of F, but that's kind of obvious. But, okay, just to be complete. So, that's pretty obvious. So, the of F part, anyway. So, as h goes to 0, now, guys, if we let h move towards 0, this point right here, this Cartesian point, is going to move. It's going to move. So, h is, instead of letting h be a still fixed value, we're letting h move now. And in other words, we're taking a bead, which is a point, and we're moving it along our graph. And this bead, we're moving it arbitrarily, indefinitely close to CF of C. We don't want to let it actually arrive at CF of C, but we want to let it get indefinitely close. As h is shrinking more and more towards 0, this point is honing in more and more slowly on this point. And that secant line is becoming more and more like my tangent line. It's becoming more and more similar as h is going to 0. Now, here's the thing. So my difference quotient is becoming more and more like my derivative. So we're taking the limit as h goes to 0 of this difference quotient to get our derivative. The difference quotient goes with the imperfect secant. The derivative goes with the perfect tangent. The secant's not perfect or imperfect. The tangent is perfect. The difference quotient is imperfect or kind of crude. The derivative is perfect. It's very pristine. So we're taking a bead whose Cartesian coordinate is this, and we're moving that bead toward CF of C, aka we're letting h go towards 0. H is going more and more towards 0. We don't let it hit 0, but we let it get arbitrarily close to 0. Okay, and our secant line is becoming more and more like our tangent line, and the slope of our secant line, which is the difference quotient, is becoming more and more like our derivative, which is the limit of the difference quotient as h goes to 0. That's a summary thereof of everything we've said so far. Okay, let's pull up Excel. My time is getting quite short. Now, here's y equals x squared. Now, here's just a fixed secant line. Y equals negative 5x minus 6. That's the red line. My red line is my secant line, and it's passing through negative 3, 9 and negative 2, 4. Now, the point I want to focus on, first off, is negative 3, 9, just because I want to. Notice that negative 3, comma, positive 9 is on the parabola y equals x squared. After all, if you square negative 3, you'll get positive 9. So, and indeed, here's my x coordinates here, my y coordinates here. And so negative 3, 9 is there. And another point that's going to serve me well, even though it's not my point of focus, is negative 2, 4. Now, let's say that I want the red line that passes through negative 3, 9 and negative 2, 4. I want the equation of that red line. So the equation of that, to get the equation of that red line, what I do, I need to get the slope. Remember from algebra, I do f of neg 2, which is 4, minus f of neg 3, which is 9, over negative 2 minus a negative 3, which is going to amount to positive 1 on the bottom. Now 4 minus 9 is neg 5. 2 minus neg 3 is positive 1, but neg 5 over positive 1 is neg 5. I do all the math right here. Now, if I hit this, f of neg 2 minus f of neg 3 over neg 2 minus neg 3, this is my red secant line, and it's red. That's going to be 4. F of neg 2 is 4, f of neg 3 is 9, over neg 2 minus neg 3. But if I minus a negative 3, remember that's plus 3, and negative 2 plus 3 is positive 1. So that's all I'm saying right here. And now 4 minus 9 is neg 5 right here. And negative 5 over that positive 1 that we got is itself negative 5. I'm going to have to stop the video. I'll continue this on the next video. Thanks.